Hello everyone. In this session, let's get some amount of understanding regarding the support vector machines. This is one of the newest technologies which has enabled machine learning into new dimensions altogether. So, one of the major elements of machine learning which can be used for classification of the data as well as for numerical predictions. So typically two major branches of supervised learning, the classification as well as numerical prediction, both of them can quite comfortably be accomplished using the support vector machines. So when we use the support vector machines for classification purpose, we call them as support vector classifications, and when they are used for numerical predictions, we call them as support vector regression kind of models. So this is what we would like to understand. Initially, first of all, how does the support vector machine get into the process of machine learning? First of all, what is support vector machine? How does the support vector machine get into the process of machine learning is something that is very important to understand before we start using the different algorithms in R and executing them to data sets to try to accomplish our exercise of classifications and numerical predictions. So this is what we would like to look at in this very small session. We would talk about a basic introduction to the world of support vector machine and how does that support vector machine typically get into the process of learning from the data. What is the typical mechanism that the support vector machine learns from the data? And then we also talk about the general transformations which are typically called as the kernels. So we would be talking about the generally used the kernel transformations which the support vector machine typically uses as a part of its classification mechanisms. So just getting started, as discussed, SVM is a part of the supervised machine learning process, and it can be used for both regression purpose, which is a numerical prediction, as well as classification, which is more and more of categorical prediction. So I can use support vector machines for both the purposes. Now when they are using in a classification, this is how it is. Okay, if I talk about two sets of elements, right, one belonging to the group of blue from this diagram. Let's say we are talking about two groups. Let's say these are the defaulters and non-defaulters. I'm plotting a set of people, both including the defaulters and non-defaulters on a particular load on a graph, right? I have some variables on the x-axis, I have some variables on y-axis, and probably I could have few more variables on the z and other dimensions as well. Now what the support vector machines typically are doing is they are constructing a hyperplane. So this is a line that is typically being constructed. Now this is a linear, right? Basically in a two-dimensional space, I am trying to create a kind of a segregation between the blues and the reds. So which is a very simple classification, but just to get a good understanding, the support vector machine tries to draw a kind of a hyperplane, right? Here it is a line, linear kind of separation, but in when you are going into a multi-dimensional scenario, this line could very well be replaced by a plane. So there is a hyperplane in a multi-dimensional space that is separating these blues versus the reds, because blue belongs to a set of defaulters or probably whatever, and red belongs to a set of non-defaulters. So I'm trying to separate these two groups of people by drawing a kind of a hyperplane in between them. And once that hyperplane is created, we are looking at a decision plane, right? Whatever is the equation that is associated with it, that is used to define the boundaries. So anything lesser than this will fall into, right? We are creating an equation out of this plane, and values which are lesser than that are going to fall into the default category. Values which are higher than that are going to fall into the non-default category. So there is a decision plane which we are defining, based on which the boundaries of when an element will fall into a default category and when it will fall into the non-default category is something that we are identifying. And that decision plane is separating the set of observations into the default class versus a non-default class. So that's the way the typical support vector machines is working in terms of classification of the variables. But this looks like a very simple problem. It looks like there is a linear separation that is existing between the blues and the reds. But in real world, majority of the classification problems that we get in, I cannot simply put a linear boundary between them, right? They may be having a kind of a non-linear kind of boundary. Probably here, if you look at the blue versus the red, I cannot draw one single line which can separate both of them. So probably this kind of a curvilinear kind of separation is very much required here. So this is what I am calling as a non-linear boundary. Now, what happens when such kind of non-linear relationship exists between the values is, there is some kind of mathematical function, right? Some kind of mathematical functions like, okay, logarithm or exponent. Some kind of mathematical transformations are being performed on these observations, so that after executing that mathematical function, we get that they are linearly separated. So the input data, even though it is having a non-linear relation, we can apply some set of mathematical functions on this data, which is having non-linear relationship between the classes. We are doing some kind of a transformation, and because of this transformation, it's very much possible that I can create a linear boundary separation between the observations. So those kind of functions that I am applying on the input data, so that transformed values are resulting into a kind of a linear separation between the observations, are typically called as kernels. We have different kinds of mathematical functions. Different tools will use different sets of kernels. They support different sets of kernels for transforming the data from one form to the other, right? So the values which are there in the original input space, they would be transformed into new values which will go as a part of the feature space, and the transformation between the values is typically observed. Now this transformation, when we use the word transformation, it is nothing but it's a kind of rearrangement of the values. By applying some formula, we are rearranging. So which means each of this, so this is the input object, and once I have performed a transformation on it, it becomes this. So there is a one-to-one mapping between the original variables versus the ones that I would be transforming them into. But after they are transformed, I should see that the objects are majorly linearly separable. That is the major thing that goes into the support vector machines algorithms, right? So basically, it is using the linear learning methods itself, because initially it has transformed the data, and once it has transformed, the learning is typically becoming linear itself. Initially, the data is having a nonlinear relationship. It has applied its nonlinear kernel function, and using that nonlinear kernel function, it has transformed the variables values in such a way that it can do a linear learning method on that set of values. So that's the reason, though it is using a linear learning method, we still call it as a non-linear classifier, because internally the kernel functions have transformed the non-linearity relation that is existing between the variables into a linearity kind of a relation, right? So if you see here, each object which is there in the input space is mapped into the feature space. Then the class boundaries are also defined accordingly. So this is the boundary. So this entire line is a boundary line. Even that boundary line is also mapped, which is resulting into a linear relationship out here. And all the objects which are both into the blue as well as the red, they are mapped into the feature space by that particular kernel function. So understanding the different kernel functions is very much important, because that particular kernel function is transforming the data from its original form into a new form, so that the different categories are linearly separated. When it comes to the implementation part, of course, we are not getting too much into the mathematics of it. By now itself, you should have got a clarity on how the support vector machine is typically working. So the process wise, the support vector machine is trying to identify that decision hyperplane, which is separating the largest gap, right? Leaving the largest possible fraction of points of the same class. So if we are talking about two different classes, right here, I want to a large extent all the reds falling into this class, and majority of the blues falling into this class. Obviously in real world probably there might be one blue out here, there might be one or two reds out here. But my objective is try to find such kind of a hyperplane where maximum fraction of the points belonging to red group, belonging to the group of defaulters, they lie on the side of the defaulters, and maximum number of people who are non-defaulters, they lie in the side of the non-defaulters. And at the same time, the distance between the classes also need to be much larger, right? Here if you see, this is the line, right? So the distance, probably I could have drawn this kind of a line, or I could have very much drawn slightly, right, slightly this line. Now what I really want to see when we are drawing a line is the distance between the groups should be as much larger as possible, because even tomorrow with some other kind of characteristics the data comes in, still I should be able to segregate between the groups quite comfortably, because here we have done the decision plane using the training data, so that with respect to the training data probably the separation between the groups could be quite comfortable. But when I am trying to use a new data altogether for testing purpose and the same model, it might very well be possible that the classification may be misleading. So I don't want to enter into the risk of misclassifying those elements just because I have found out some simple solution which is separating the values into the two groups. I want the best possible separation distance between the two groups, so that even some kind of abnormalities can be handled quite comfortably. So mathematically, the support vector machines get into an iterative training algorithm, and they minimize an error function. Error function is the error with respect to the misclassification of the elements into the different groups. So that particular misclassification is trying to be minimized. So if you look at it, the transformations are applied in such a way. If you look at the features, So xi is a set of features, right? So probably now we are trying to do a classification based on the various features, right? Let's say I want to classify the defaulters versus the non-defaulters based on the age and the amount of loan and gender that they belong to. So this will be my x1, x2, x3. So these are the three feature vectors that I have. The target is either the person would have defaulted or non-defaulted. So in support vector machines, I have to give them as -1 or +1. -1 in case of negative and +1 in case of positive. Right? And now our objective is look at a function of x and alpha. Choose some kind of alpha, and k is your transformation function, which is what we have been calling as a kernel function, right? So we can very well see the decision function for classification of the unseen variables goes like this: sine of alpha I, so this is alpha I, alpha I yi, k of si comma x, oh this is si only, plus b. Now we are talking about support vectors. Si is a support vector, right? The support vectors are the ones that are typically falling on the boundaries of each of the maximum distance. Now if you say this is my optimal hyperplane, I'm seeing, okay, to what extent the first one of this particular group and the first one of this particular group, what is the kind of distance that is existing between them. This is called as a support vector. This is also called as a support vector. And the distance between these support vectors is the kind of a margin that we are talking of, right? So we have a kernel function. So we have, if I'm talking about two different groups, we have two different support vectors, SIs. So these are the two different support vectors, one for the blue and one for the red. And we also have a kernel function. So we'll talk about the kernel functions very soon. So there is a transformation that is getting applied on your yi values. Based on your yi values, there is a transformation function that is getting applied, and the parameters are determined by maximizing the margin hyperplane, because I want this margin to be the maximum most possible, the separation distance between the group to be maximum most possible. And based on this alpha and b are typically computed, and this is what is the maximizing process that is being followed. So the constraint, so this is the mathematics part of it, but business wise, if you are trying to understand, I want to understand the optimal hyperplane and determine the parameters of the plane in such a way that the margin distance between the planes is maximized. And in turn, we can also use a cost parameter. The cost parameter is majorly in terms of what is the kind of a misclassification rate. Error part is what is going into the cost function. So depending on what kernel, see, I want to choose a kernel function in such a way that my cost parameter is the least possible. And based on that cost parameter also I can determine what are those alphas and betas which can minimize my overall misclassification rate. So what is the margin? So we are talking about the maximizing margin between the two groups, but at the same time I want the misclassification error to be the least possible. So we are trying to get into the trade-off between these two activities. I am determining the kernel function in such a way that the misclassification error is as less as possible, But at the same time, I'm also looking like the distance between the groups should be as high as possible so that even in future a new observation requires a classification, we can do it with little amount of error. So that's the kind of process that is followed. So the whole process is heavily based on the kernel functions that we are going to use. And in this case, very commonly used kernels, once we look at the R implementations of each one of them, we would see that the different implementations of R, they support different kinds of kernel functions, right? Probably from our perspective, use as many different kernel functions as possible, right? And with each of these kernel functions, try to build a model, and once the models are built, try evaluating them on the test data, and whichever the kernel function has really given us much more appropriate result on the test data, we would be using that particular result for the prediction purposes. So we'll try to understand some very commonly used kernels. So there could be a linear kernel where the transformation typically happens in this way: the original vector, there's a transformation and multiplying with into a new one. This is a polynomial transformation, so you could see something raised to the power of d, and gamma is a parameter which is used as a multiplier in front of the original parameter value. Similarly, you could have a radial basis function which is more similar to that of the assumptions of normal distribution. Then you have a sigmoid kernel which is doing a hyperbolic tangent transformation. Gamma, R, different kinds of parameters are being used in each of the transformations, but those parameters are very well determined based on the minimization of the error or the misclassification rate. So rather than getting into the mathematics, of course, there's a different way of understanding both of these things. One, you can understand the mathematics behind them. Two, we can very well look at the business side of them. All I need to understand when I'm going with a support vector machine is that my data gets transformed, right? And that transformation, I can apply any of the different kinds of transformations on the data. So depending on the kind of transformation that I am applying, after that an SVM, if it is run, I could really see to what extent is the model that we have fitted trying to estimate the test data. What is the accuracy of the model with respect to the test data? And whichever the transformation has resulted in a higher amount of accuracy or the lower amount of misclassification rate on the test data, that would be the choice for our future prediction purposes. So that should be the business understanding of the support vector machines and the various kernels used for the business interpretation purposes. So this is what is a very small session which I wanted to bring an input, bring your attention to in terms of the understanding of the process of support vector machines. If you have any further queries, request you to give me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.